Hello friends, welcome to the channel Physics by IITians.
Hello friends, this is revision class and in this class I shall discuss about the most important topics about the nuclear and particle physics, and you from this video you will get short note on nuclear physics, and this is totally give you a revision before your NET GATE examination. So friends, you can have free test in our portal. For that you can register here. Okay, please note down this link and it is also given in the description box. Please note down this and you will get the opportunity to give a free test, and also full solutions are also available, and we are also guiding you for the PhD integrated PhD admission, for the interview also. So for more information contact us on Telegram channel. So friends, let's start the video. In this class I shall focus on nuclear structure and general properties of nuclei. So first of all, you all know about the constituents of nuclei. So atomic nuclei are composed of two different types of elementary particles. One is proton and another is neutron, and collectively the neutrons and protons are referred to as nucleus. The proton is identified as the nucleus of the lightest and the commonest isotope of hydrogen. It carries only one electronic charge, that is plus E, and has a mass about 1836 times the electronic mass of electron, or Me. The neutron on the other hand possesses no charge, that is electrically neutral, and its mass is almost same or equal to the proton, but it is slightly heavier than proton, and the electronic mass is negligible compared to proton or neutron. Now according to Coulomb's law, the positively charged protons closely spaced within the nucleus should repel each other strongly and they should fly apart. But nucleons, that is where they held together the protons and neutrons, because there is a influence of very strong short range attractive force. So this force is different from commonly known forces as gravitational, electrical, or weak forces. So this nuclear force is classified as the strong interactions. Or you already know that whenever there is a nucleons, so there will be pi meson which will play a role in this making nucleons, that is protons and neutrons together inside the nucleus. The number of protons in the nucleus determines the atomic number of the nuclei, and the sum of the numbers, that is the protons, that can be denoted as Z, and neutrons, that is N, inside the nucleus is the atomic number. So A equals to N plus Z, and the neutron number capital N is A minus Z, and we can denote symbolically a nuclei by this symbol, that is ZXA, where X is the atom, Z is its atomic number, A is its mass number. And it is three different definitions of isotopes, isobar, isotones you should also remember. So what is isotope? That is nuclei with the same atomic number Z but different mass number A are called isotopes, like lithium 36, lithium 37. Although they both have 3Z, but 6 and 7, that is mass numbers, are different. Similarly, Ne 1020, 10 Ne 22. Now, nuclei with the same mass number but different atomic number Z are called isobar, like oxygen 816, nitrogen 716. So look here, although their mass numbers are same, that is 816 and 16, but different atomic number Z. Nuclei with the same number of neutrons, that is having the same number of N, those are known as isotone, like sodium 1123, magnesium 1224. So they both have same number of neutrons. And what is the mirror nuclei? The pairs of isobaric nuclei such as 6C11 and 5B11 or 7N13 and 6C13 are known as mirror nuclei, in which the proton number Z and the neutron number N are interchanged and differ by only 1 unit. So here the proton number is 6, neutron number is 5. Here the proton number is 5 and neutron number is 6. So they are actually interchanged and differ by only 1 unit. So this type of nuclei are called mirror nuclei. You all know about nuclear mass, binding energies. Let's know that once again, just for your information. The nuclear mass is the M nuclei is obtained from the atomic mass M, which is A, Z, is subtracting the masses of Z orbital electrons. That is, mass of nuclei equals to atomic mass minus the mass of the orbital electrons, that is Zm. And the above expression, however, is not exact in that the binding energies of the electrons have not been taken into consideration. Only we have taken the mass of the atoms and we just subtracted the mass of the electrons. But we also know that we should consider the binding energy of the electron. So in forming a nucleus, what is that? What is binding energy? So suppose you have some constituent particles and you want to form a nuclei out of these constituent particles. Okay, so a fraction of the total mass of the constituents disappears and evaluation of energy equal to EB takes place. So if there are just certain constituents like certain protons, electrons, neutrons are there, but can you make this to an atom, or can you make out of it to an atom just making them together? No, you need some energy, and this is called binding energy, which will make them bound and which will give the shape of that atom. So delta M is that kind of amount of mass which is disappeared due to this forming of the binding energy or due to this binding energy. So this binding energy EB can be written as delta M into C square. So if MH, Mn be the masses of the hydrogen atom and neutron respectively, then delta Mn equals to ZMH plus Nmn minus Ma, Z, where MAZ is the mass of the atom of mass number A and atomic number Z. So binding energy expression will be ZMP, that is mass of proton, plus Nmn, that is total mass of neutron, minus M nuclei into C square. So out of, suppose there are 6 protons in carbon atom, 6 neutron in carbon atom. So first of all, take individual mass of the protons, neutrons, and then take the mass of the nuclei and make the difference, take the difference out of them, you will get the energy, that is binding energy. What will be the units of atomic mass? The unit of atomic mass is presently defined to be 1/12 of the mass of the atom of carbon isotope C12, taken to be exactly 12 units, and is symbolized by small u, being the abbreviation for Unified Atomic Mass Unit. So 1 AMU is 1.660566 into 10 to the power minus 27 kg. And if you want to express in MeV, that is energy equivalent of AMU will become 931.501 MeV. So you all should remember that 1 AMU is 931 mega electron volt. So what will be the energy equivalent of the rest masses of the electron, proton and neutron? For electron, Me is 9.1 into 10 to the power minus 31 kg. In AMU, it will become 5.48 into 10 to the power minus 4 AMU. For proton, mass is 1.67 into 10 to the power minus 27 kg. In AMU, it is 1.0072 AMU. For neutron, it is 1.67495 into 10 to the power minus 27 kg. This is 1.008665 AMU. Okay. So whenever, if the binding energy is positive, that means the nucleus is stable, and energy from outside is to be supplied to disrupt the nucleus into its constituent separately. But if mass binding energy is less than 0, that is negative, the nucleus is unstable and it will disintegrate to itself. So E value, that is the binding energy value, EB value, is a measure of the stability of the nucleus. So more the EB, the more is the stability. What is mass defect? Mass defect is the difference between the measured atomic mass, that is MAZ, expressed in U, that is atomic unit, atomic mass unit, and the mass number A of the nuclide, that is delta M prime equals to MAZ minus A. Suppose what will be the mass defect of helium-4? So the mass defect of helium-4, we account the mass number for helium as 4 AMU, and the actual mass or the measured atomic mass of helium is 4.002603 AMU. So you should take a difference and you will get the mass defect of helium as 0.002603 AMU, and that for the oxygen is minus 0.005085 AMU, as the measured mass atomic mass is 15.994915 and expressed atomic mass as 16 for the oxygen. So the mass defect can therefore be positive as well as negative. It is found that the mass defect is positive for very light and very heavy atom, and it is negative in the region between these two. What is packing fraction? Packing fraction is defined as the mass defect per unit nucleon, that is delta M prime divided by A. What is delta M prime? Yes, M AZ minus A divided by A. So you can write it as M divided by A minus 1, or A M AZ can be written as M of AZ equals to A into 1 plus F. So the binding energy per nucleon EB by A or FB, that is binding fraction, is given by EB by A or FB equals to ZMH, that is binding energy ZMH plus NMH minus MA comma Z divided by A. So binding energy per unit nucleon, that is called the binding fraction. So you should understand the difference between packing fraction and binding fraction. Packing fraction is the mass defect per nucleon. Binding fraction is binding energy per nucleon. Okay. So if you put a graph, if you draw a graph, a binding fraction versus mass number. So how do you get that? It will give like this way. So let us study its characteristics. So FB, that is the binding fraction. Okay, this is FB, that is EB by A, and which we are plotting EB by A, that is FB, and this along x direction, this is A is plot, that is atomic mass. So binding fraction or FB is very small here. Look here, this is very small for very light nuclei and goes on increasing rapidly with increasing A and reaches to a value of nearly 8 mega electron volt per nucleon for the atomic number A equals to 20, like here. Thereafter, the rise of the curve is much lower. After that, it is just lowerly increase. Okay, and then it will decrease slowly like this way, and it will be after A equals to 56. The variation of FB, that is the binding energy per nucleon, is very slight in the mass number range from 20 to 180, and in this region FB may be considered to be virtually constant with a mean value of 8.5 mega electron volt per nucleon. Now whenever A is greater than 180 degree, that is very heavy nuclei, this packing fraction, binding fraction value FB decreases monotonically with increases. So look here, what does it mean? That is binding energy is decreasing with increasing number of atomic number or for the heavy atoms. So the nucleus is not so much stable. So for A greater than 0, it is nearly 7, A greater than 180, it is nearly 7.5 MeV per nucleon for the heaviest nuclei. A rapid fluctuation in FB is noted for very light nuclei, where this is a rapid fluctuation, this increase is rapid, and with peaks in the curve of the region corresponding to even nuclei. So binding energy or EB by A is higher means these nuclei are highly stable. Like which nuclei are highly stable? Where there is occurring peaks in this graph. So in this curve like helium-4, beryllium-8, carbon-12, oxygen-16 with mass number A equals to 4n, where n equals to 1, 2, 3 peaks in this curve as also seen at Z and N equals to 20, 28, 50, 82, 126, and these are called the magic numbers. So hopefully you understand that whenever in this curve, what is the significance of this curve? The significance of this curve will give you the stability of the nucleus, that what are the stability, that whenever there are the peaks in this curve, those nuclei are much more stable, because from the definition that binding energy, the binding energy is more means Fb will be more. So binding energy is more means the nuclei are more stable, and this heavier side the binding energy is going lower, the curve is going lower, means they are less stable, and whenever there are peaks occurring means they are most stable, and these peaks are at mass number A equals to 4n, and these are known as the magic numbers. What is the nuclear size? So nuclear actually experiments, if you perform certain experiment, nuclear can be assumed to be spherical or nearly spherical, but not exactly spherical. So how do you measure that? The radius of the R, if we think the nuclear radius as capital R, and you can think that R is proportional to a to the power 1/3, where A is the mass number. So what will be the proportionality constant? The proportionality constant is R naught. Okay, or you can think that A equals to V is proportional to R cube. Okay, so yes, from that relationship also you can get this relationship, or you should understand that this proportionality, that is R naught, is called the nuclear radius parameter. And what is the value of R naught? That is ranging from 1.1 to 1.5 10 to the power minus 15 meter, or 1.1 to 1.5 femtometer range. So what is the radius range of the nucleus? That is 10 to the power minus 15 meter range. So how much smaller is it, right? Atomic radii is Bohr radius. If you take, then you get 0.5 angstrom, that is 0.5 into 10 to the power minus 10 meter. And now nuclei range you are taking as 1.1 to 1.5 into 10 to the power minus 15 meter. So since the nuclear charge parameter here Z is proportional to the atomic number A, the nuclear charge density rho C is nearly the same throughout the nuclear volume. The distribution of nuclear charge plus ZE follows the pattern of nuclear mass distribution. So the charge radiation we can take also same as the mass radius of the nuclei, means the charge is distributed uniformly throughout its radius or throughout its volume. The size of the nucleus was first estimated from Rutherford's alpha ray scattering by various atoms, and he showed us in his experiment that the radii of the nuclei, or the size of the nucleus, is much smaller than the radii of the orbits, electrons orbit. The larger of the angle of alpha particle scattering is thus closer to its approach to the nucleus, because there will be maximum scattering due to the Coulombic interaction. So if we take that the energy of that scattered particle is kinetic energy is half mv square, so at the maximum repulsion, that is kinetic energy equals to potential energy of the so it will be half mv square equals to twice c, that is the charge of the helium or alpha particle, helium nucleus or alpha particle, into Ze, that is the charge of the nuclei, that is plus Ze, divided by 4 pi epsilon naught r, where r is the distance of the closest approach. So this is a very important formula. You should remember that r is Z square by pi epsilon naught mv square. So whenever there is the distance of the closest approach, you should equal the kinetic is equals to the potential energy, and from that relationship we get the value as r equals to Z square by pi epsilon naught mv square. What will be the mean squared radius r square average of nuclear charge distribution? This is given by 3 by 5 into capital R square. So for suppose a uniformly charged sphere of radius, then capital R is constant. So rho, that is the charge density, will be constant for inside the radius, and rho should be 0 for outside the radius or outside the radii of the nucleus. So since this is a nucleus is a charged particle, so it will have also magnetic moment because it is moving So whenever there is a magnetic moment, we should define it, and we should define in terms of the magneton. Just like electrons with as Bohr magneton, for nucleus the angular momentum associated with the nucleus we termed as nuclear magneton. And what is the value of Bohr magneton? Bohr magneton value is EH cross by twice pi m, and for nuclear this is EH cross by twice m. It is EH cross by twice me. It is EH cross by twice mp, or it can be written as EH by 4 pi me, and this is for the nucleon, it can be written as EH by 4 pi mp. So the different quantity here, just the mass of the electron, and this is the mass of the proton. So which one is larger? This one is larger, as this mass of Me is smaller. So this is 9.2 into 10 to the power minus 24 joule per Tesla. This is 5.05 into 10 to the power minus 27 joule per Tesla. So what we have seen here, that nuclear magneton is basically 1836 times, that is 1836 times smaller than the Bohr magneton, and it is also called the Rabi magneton. The magnetic moment of proton is not one nuclear momentum magneton. It has instead a moment plus 2.79 mu1. And this positive sign indicates that the magnetic moment vector mu coincides with the angular momentum vector I. And these are all the things that you should know about what is the gyromagnetic ratio, and what will be that. Gyromagnetic ratio is the net magnetic moment mu of a nuclei depends on the resultant total angular momentum of the nucleus. So mu, that is the net magnetic moment, is gamma into I, where I is the total angular momentum of the nucleus. So it can be written as G into mu1 into I, where gamma is the product of the gyromagnetic ratio and the nuclear magneton, mu1. Okay. So we have also assumed that the nucleus is spherically, maybe the shape of the nucleus may be nearly spherical, but actually it is not spherically symmetric in shape. Rather, it has electric quadrupole shape. Okay. So it can be derived. Okay. So it is some deviation from the spherical shape, and this is what is called as electric quadrupole moment, capital Q. We can derive it. So suppose let a charge of nucleus of charge number Z, and it is deformed from a spheroid to an ellipsoid shape. So it is not spherical, and we are taking the consideration of the deformation from a spherical shape to a ellipsoid shape. And the ellipse major axis is 2a, and this is the perpendicular to the symmetry axis, and the minor axis to be 2b, that is along the axis of the symmetry. Then the quadrupole moment capital Q for such deformed nucleus is 2 by 5 z into a square minus b square. And if r is the average nuclear radius and delta r is the deviation of capital R from the direction of symmetry axis, then capital Q can be written in terms of r and delta r as 6 by 5 z r square into delta r by r. So if you find out in terms of the density, charge density, that is, suppose we are taking rho as has coordinate xyz with the volume density of charge of the nucleus with its center of mass at the origin, then we can take r square as x square plus y square plus z square, and the quadrupole moment Q will be defined from the electrostatic energy from the interaction of electric potential and the charge density, and we can take Q as 1 by E integration of 3z square minus r square rho d tau, where this integration is carried out over the entire volume of the nucleus, that is d tau, and E is the charge of the proton, and nucleus is assumed to have a symmetry along the z axis. Okay. So please friends, I request you to consult a book, Nuclear Physics, S.N. Ghoshal. You will get all this derivation from that. We can, so whenever we are considering as a quadrupole moment, so basically this is, if we consider the spherically symmetric nucleus, the figure will be like this way, that is the symmetry, line of symmetry along z axis. But if suppose you are taking thus not spherically symmetric, but suppose it is a deformation of sphere, it has become a ellipsoid. So the ellipsoid can be like this way, or the ellipsoid can be like this way. So this kind of ellipsoid is called the prolet ellipsoid. For this, the capital Q is greater than 0, and this kind of ellipsoid is called the oblate spheroid or ellipsoid. This is called Q is less than 0. Okay, and also you should know that Q here for the measurement of the nuclei, the capital Q is measured in terms of burns, and one burn is 10 to the power minus 28 meter square, and capital Q will be 0, that is total charge will be 0 for a spherically symmetric nucleus. Okay, suppose there is a s orbital. For s orbital, we always take the dipole moment as 0, like the hydrogen atom, because the charge is spherically symmetric. So spherically symmetric, the total charge Q is 0. So whenever there is a total charge Q is 0, so there is no dipole moment. But for P, for D, we have to consider the charge of the, this is I am telling you overall the atom, not the nucleus case. But here we are considering only the nucleus case. But we are kind of, there's an analogy between the shape and the charge. Okay. So the magnitude of capital Q, that mostly lies in this range, that is 10 to the power minus 28 meter square to 10 to the power minus 30 meter square, and depends on the radius and charge of the nucleus and its deviation from the spherical symmetry. Now, if you want to take the spin angular momentum, so both proton, neutron, like the electron, they have intrinsic spin. So the total angular momentum can be written as Ls equals to root L into L plus 1 H cross. Where this spin quant is since these are fermions, so it is half integral spin. So the spin angular momentum has a value root 3 by 2 H cross. So we have our full length test series, friends. With rupees 249, you will get 5 tests with solution, and these are totally timer based test series. You will give like just like real net examination, gate examination. So if you are preparing for the JAM, JEST, gate examination, this topic wise test series will be extremely helpful for you. It costs only 549 rupees, and for 10 tests. And combined test series costs only 699, that is a 15 test subjective full length with solution, everything is given. So link has been given in the description box. Click on the link, and for more details contact us on our Telegram channel, also on our email ID. So everything is given in the description box. So nuclear spin we have already discussed. Now parity of nuclei, you all should know about this parity. So there are two kind of parity are possible, basically even parity and odd parity. So if this exchange of coordinate, that is psi of minus x minus y minus z, the wave function will come back to its original value, that is at psi of xyz. This is called even parity. But if this psi at minus x minus y minus z will not give psi, but it will give minus of psi xyz, this is odd parity. So the particle moving with a large velocity, can be quantum mechanically associated with a wave. So this wave motion can be described by the wave function psi, and this depends on the space coordinates like x, y, z. So if there is a change in exchange of the space coordinate, the change in the wave function is occurred, the change in the sign, then it is called odd parity. If there is a no change in the sign occur, then it is called even parity. And the parity pi is determined by the orbital quantum number, that is pi can be written as minus 1 to the power L. So if L equals to 0 or L equals to 2, L equals to 4, the parity is even. But if L equals to odd, that is L equals to 1, 3, so 5, so then parity will be odd. So we all know about Rutherford alpha ray scattering experiment. I am not going to tell you the details about this experiment, but basically I am giving you the formulas that you should remember, that what is the collision parameter or impact parameter, that is the minimum distance to which alpha particle would approach the nucleus if there were no force in between them. So Q is b cot theta by 2, or Q equals to b into 1 plus cos theta divided by sin theta. So b is here basically the collision parameter, and k is currently the k value is z into e into capital E by 4 pi epsilon naught mv square, that is the closest approach. E is the charge of alpha particles, and the angle of scattering is phi. Our unit solid angle W phi equals to k square 1 by 4 sine to the power 4 pi 5 by 2. So let us take some examples. Whatever we have read here, we should know how to implement whenever we face some problems and how to implement those formulas and find out the answers. So the question is, calculate the binding energy in mega electron volt of helium-4 from the following data. So you have to calculate the binding energy in mega electron volt. So in energy unit, not in AMU. Okay. And the given data is mass of helium is 4.003875 AMU, mass of hydrogen 1.008145 AMU, mass of neutron 1.008986 AMU. So helium-4 nucleus, it has 2 protons, 2 neutrons. So the mass of the constituents means that 2 proton mass plus 2 neutron mass. You have to first calculate this. So 2 into 1.008145 plus 1.008986, you will get 4.034262 AMU. Now mass of the helium nucleus as given here, that 4.003875 AMU. So the mass difference, that is the binding energy, you have to find out. So the constituent mass minus the mass of the nucleus. So the constituent mass, this 4.034262 minus the mass of nucleus, helium nucleus, that is 4.003875, you will get 0.030387 AMU. And binding energy EB will become, this is in AMU unit, so you have to convert it into mega electron volt. Now 1 AMU equals to 931 MeV, so 0.030387 AMU is 0.030387 into 931 mega electron volt, and it will give you 28.29 mega electron volt. So this much amount is the binding energy of the helium nucleus. So if you can just somehow separate out helium nucleus, you will get minimum amount of energy is 28.29 mega electron volt. So just assume that how much energy is just within this binding energy. Okay. You should visualize whenever you are reading something, you should understand what can be the applications or implications of these results. So that let us take another example. The mass of the hydrogen atom and of neutron are 1.008142 and 1.008982 AMU respectively. So you have to calculate the packing fraction and the binding energy per nucleon of oxygen, that is O16 nucleus. So oxygen O16 nucleus, 8 protons, 8 neutrons. First of all, calculate the mass of the constituents. That means mass of 8 protons plus mass of 8 neutrons. You will get it as 16.136992 AMU. Now mass of oxygen 16 has been given as 15.994915 AMU. So mass difference or mass loss is the difference between the constituents and mass of the oxygen nucleus. You will get it as 0.142077 AMU. So binding energy EB is, in terms of mega electron volt, will be 0.142077 into 931 mega electron volt, that will become 132.27 mega electron volt. What will be the mass defect? Mass defect is, that is mass that is measured, that is for the oxygen O16 nucleus, that is 15.994916, and the mass number, that is 16. So you take the difference and don't put the negative sign. Okay, so it is just you are taking the difference, you are ignoring the negative sign here. So you will get as 0.005085 AMU. What will be the packing fraction? Packing fraction is mass defect per nucleon. So mass defect is delta M, nucleon is A. So 0.055085 divided by 16, it will give us 3.178 into 10 to the power minus 4. So these are very easy questions. Just apply this little formulas, understand and do some conversion of units, you will get easily the answer. So let us take another example. The radius of a copper nucleus is measured to be 4.8 into 10 to the power minus 13 centimeter. Find the radius of magnesium nucleus. That is copper nucleus, the atomic number 29, this is 64 and this is 1227. So we know that R is R naught into 10 to the power 1/3. Earlier it was small R naught, now it is written as capital R1, R naught, but these are all the same. Okay. So R equals to R naught a to the power 1/3. So R1 can be written as R naught a to the A1 to the power 1/3, and R2 can be written as R naught A2 to the power 1/3. So R1 is given as 4.8 into 10 to the power minus 13. So it is equals to R naught into 64. This is the atomic number. So 64 to the power 1/3. This is the mass number. So R naught will become 1.2 into 10 to the power minus 13. And so for the finding out the radius of R2, that is the magnesium nucleus, you will have to put the value of R naught, that is 1.2 into 10 to the power minus 13 into A2 to the power 1/3. So that is 27. This is A2 to the power 1/3. Ignore this by, this is nothing, this is into. Okay. So it will give R2 equals to 3.6 into 10 to the power minus 13 centimeter. So option C is the correct answer. So another question, that's since this silicon, that is 1427, and aluminium 1327, these are mirror nuclei. Why these are so? Because look here, the proton number and the neutron number are exchanged and differ only by 1 unit. So now they are mirror nuclei. Okay. So these ground states are identical except for a charge. If their mass difference is 6 mega electron volt, estimate their radius, neglect the proton neutron mass difference. So the mass difference between mirror nuclei can be attributed to the difference in electrostatic energy. So now the electrostatic energy of a charge capital Q distributed uniformly throughout a sphere of radius r, and this is the electrostatic energy, that is W equals to 3 into Q square divided by 5r, where capital R is the radius and Q is the charge that is distributed uniformly throughout the nuclear or the sphere, if we assume that the spherical distribution. So the delta W, that is the change in the electrostatic energy, is 3e square by 5r into z1 square minus z2 square, because the at mirror nuclei they only differ by the amount of 1 unit of charge, right? So we can write that Q1 as e square into z1 square and Q2 as e square into z2 square, that is Q1 square and Q2 square. Take the difference between them and you put the values, and you will have to put in form of the given MeV unit. So you need to know the fine structure constant, that is E square by Hc is 1 by 137. So put these values, you will get R, that is the radius of this mirror nuclei, as 388 femtometer. Okay, so look here what we have done here. So that's all for you to understand how to calculate. So E square by Hc you have taken here, so you have to multiply here also by Hc factor and just calculate and simplify it. That's all you need to find out the result of this kind of questions. The simple formulas you have to apply here. Another question from Rutherford experiment. A particle of energy 5 mega electron volt is scattered through 180 degree by a fixed uranium nucleus. Calculate the distance of closest approach. So what will be the distance of closest approach? That is the kinetic energy of that alpha particle is equals to the interaction, Coulombic interaction or Coulombic potential energy. So the d is the distance of the closest approach is z square divided by pi epsilon naught mv square. V, you have to find out the particle energy 5 MeV, from you have to find out the velocity, and z has been is 92, that is uranium nucleus proton number. E square as 1.6 into 10 to the minus 19 whole square, pi is 3.14, epsilon naught is 5 into 10 to the minus 12, and 5 mega electron volt in terms of Coulombic unit, you have to write. So joule. So this is divided by 1.6 into 10 to the power minus 19 coulomb. Since it is in MeV, so 10 to the power 6 will be here, 5 into 10 to the power 6. So it will give us 1.6 into 10 to the power minus 13. So after calculating, you will get it as 5.3 into 10 to the power minus 14 meter. So this is your exercise that calculate the binding energies of the following isobars and their binding energy per nucleon. Given the nickel mass as 63.9280 AMU, copper 63.9298 AMU, Mn 1.008665 AMU, Mh 1.007825 AMU. You have to calculate, please don't look at this answer. Calculate the binding energy and calculate binding energy per nucleon, means the binding fraction. And also find the energy release or if one hydrogen means nuclei can fuse together to form 2 helium-4 nuclei. How do you find it? So there are a fusion, okay, nuclear fusion. So there are 2 hydrogen nuclei, they fuse together and they form 1 helium, that is 2He4. So the binding energy per nucleon of 1H2 and 2He4 is 1.1 MeV and 7.0 MeV. So first of all, you should know the number of nucleon in helium 4 is 4. 2 proton, 2 neutron. So the binding energy of 2He4 is 28 MeV because 1He4 binding energy per nucleon is 7 for helium. Now binding energy for 4 nucleon is 4 into 7 MeV, that is 28 MeV. Now equivalent energy of mass of 2He4 is the mass of the constituents minus the mass of the atomic number, that is this one, that is here. So it will give you this equivalent energy. For the equivalent mass of the hydrogen nucleus, you have to take account for the mass of the constituents, or the energy of the constituent, not here mass, because mass into energy is the mass into c square. So it has been converted to energy. So you are finding out the equivalent energy. So that is equivalent of mass of 2He4. And you are also here you are considering the equivalent energy of mass of 1H2. So you will get, then you have to compute the difference between the mass and you will get it as 23.6 MeV. So hopefully from this example you have some idea about the binding energies for the fusion energy. Okay. So friends, you can join our Telegram channel for updates, and thank you for watching this video. The sharing of knowledge is the best way of helping the society. So please join and subscribe to our channel. If you like this video, also share to your friends also, and join our Telegram channel for daily quizzes and more research articles. Thank you.